આજની આ બીએસસી માટેની આંકડાશાસ્ત્ર વિષયની બાયસેકની શ્રેણીમાં આપનું સ્વાગત છે. છેલ્લા 2 લેક્ચર્સથી આપણે પ્રોબેબિલિટી થિયરી ઉપર અભ્યાસ કરી રહ્યા છીએ. આજે આપણે પ્રોબેબિલિટી થિયરીમાં આગળ વધશું કે જેમાં બેઝ થિયરમ શું છે. અત્યાર સુધી આપણે જે જોયું એમાં આપણે સાદી પ્રોબેબિલિટીના એક્ઝામ્પલ્સ કેવી રીતે શોધાય, કન્ડિશનલ પ્રોબેબિલિટી તો કેવી રીતે શોધીએ, જોઈન્ટ ઇવેન્ટ, ડિસજોઇન્ટ ઇવેન્ટ્સ એ બધા વાત કરી, ઇન્ડિપેન્ડન્ટ ઇવેન્ટ્સ વિશે વાત કરી. હવે આપણે કન્ડિશનલ પ્રોબેબિલિટીની અંદર બેઝ થિયરમનો કેવી રીતે ઉપયોગ કરવો, તો એ માટેની આજે જે વાત કરવાની છે એના માટે તમને હવે ગોઠી સાહેબ બોર્ડ ઉપર બેઝ થિયરમ શું છે, બેઝ થિયરમ શેના ઉપર આધારિત છે, કયા ઇવેન્ટ્સ એમાં સંકળાયેલા હોય છે, એની અમને ડિટેલ માહિતી આપણને ગોઠી સાહેબ આપશે. સેન્ટ ઝેવિયર્સ કોલેજના ડૉક્ટર ગોઠી સાહેબ.
હેલો, નમસ્કાર મિત્રો. લાસ્ટ ટાઈમ વી ડિસ્કસ્ડ about probability of any event A. Formula is R by N, favorable cases divided by total cases. Then we took one addition theorem, probability of A union B, where A and B are any two events, that is PA plus PB minus P of A intersection B. This is called addition theorem for two events. Especially when A and B are mutually exclusive, then P of A intersection B will be 0, and hence it is PA union B is equal to PA plus PB, which is particular case of that definition, third axiom actually. Now we go for generalized addition theorem. So suppose B1, B2, BK, suppose B1, B2, BK are events. This is sequence of events, k events, such that number 1, union of this bi is omega, means all bi's are exhaustive events. Second, bi intersection bj is equal to phi for all I not equal to j running from 1 to k, means they are mutually exclusive. Intersection is null set, that means they are mutually exclusive. And third condition, actually there is no need to write, but it is very obvious. If A is any event, means A is subset of omega, then A must occur with any of this bi. So event A, any event A occurs with, it occurs in conjunction with any of these bi's. So if any event A occurs with any of these bi's. So if these three conditions are satisfied, then probability of that particular event A is given by PA is equal to sigma I running from 1 to k PBI into P of A given BI. So this is the generalized addition theorem. Actually this is very obvious. See, A is any event. Since all bi's are exhaustive events, so if A occurs, then it should occur in conjunction with any of these bi, means A occurs with B1, or A occurs with B2, and so on, or A occurs with BK. Since all bi's are mutually exclusive, no element common, let us take only two, we consider just two elements, two events B1 and B2, and understand. So they are mutually exclusive, no element common. So if we take their intersection with A, then A intersection B1 and A intersection B2 are mutually exclusive, no element common. So here all bi's are mutually exclusive, and hence all A intersection bi's are also mutually exclusive, and therefore PA will be equal to probability of their union is equal to sum of their probabilities. So it is P of A intersection B1 plus etc. plus P of A intersection BK. So this is sigma I running from 1 to k P of A intersection BI. Now P of A given BI is equal to probability of A intersection BI upon PBI, remember that each PBI should be greater than 0, at least it should not be 0. Then in that case, P of A intersection BI is equal to PBI into PA given BI. So substituting this value, we get this result. So this is the proof of this generalized addition theorem. But let us take a particular case. Suppose instead of K, suppose we have two events only, B1 and B2, such that their union is omega, means B1 and B2 are mutually exhaust events. Their intersection is null set, and A occurs with B1 or B2, then probability of event A is equal to PB1 into P of A given B1 plus PB2 into P of A given B2. So this is a particular case. So now the question is, when to apply this generalized addition theorem? Generally, to find probability of any event, we use this formula R by N. Then suddenly, how can we know that to find the probability of event A, we have to apply this formula? So that is the main question. So remember that if these three conditions are satisfied, then we have to apply this formula. So first condition is that B1 union B2 is equal to omega. So generally, when the sum is logical type, question is logical type, then generally we don't get union is equal to omega, intersection is equal to phi, because this is set theory approach, and generally in logical sums we don't get this type of notations. So B1 union B2 is omega, omega is certain event. So B1 or B2 union means what? So out of these two, must any one of them must occur. Omega certain event, it should certainly occur. So any one of them must occur. That is first condition. Second condition, intersection is null set. Null set, phi is impossible event. So both the events occur together is impossible. Means B1 and B2 both cannot occur together. First condition, B1 and B2 both cannot occur together. That is second. And any one of them must occur. And if A occurs with B1 or B2, then we have to apply this formula. So generally this is a usual procedure for the application of this formula. So to apply this formula, first of all, there should be, you just remember 2 or 3 things. First thing, there should be 2 experiments. Generally, we to find probability of any event, we apply R by N, and in that case, there is only 1 experiment, and we find probability of any of that event, any of the outcomes. But here, for the application of this formula, there should be 2 experiments. First experiment will have generally 2 or 3 outcomes. Just for the sake of simplicity, we assume that there are 2 outcomes. We can extend for K events also, and we have proved also. So there may be more than 2 also, but just for the sake of simplicity, we take 2 events. Suppose first experiment has 2 events. You call them B1 and B2, give their names, and for those outcomes of the first experiment for B1 and B2, you check first 2 conditions. First condition, any one of them must occur and both cannot occur together. Then there will be second experiment. Second experiment can have any number of outcomes, and we shall have to find probability of any of the outcomes of the second experiment, remember. And we call it A because we have formula for A. This is the outcome of the second experiment whose probability is to be obtained, and that must be depending upon B1 and B2. So the outcome of the second experiment whose probability is to be obtained must be depending upon the outcomes of the first experiment. So if these conditions are satisfied, then generally we apply this theorem. So just I repeat in a moment. Say there should be 2 experiments. First experiment will have 2 outcomes. For those 2 call them B1 and B2, and for them you check first 2 conditions. First condition is that both any one of them must occur, both cannot occur together, and then there will be second experiment. Second experiment have any number of outcomes. We shall have to find probability of some outcome of the second experiment, and that must be depending upon the outcomes of the first experiment, that is B1 and B2. So in that case we shall find we shall apply this formula. So this is when we should apply this formula. Now let us take one example. You just see the question on the slide. A drawer contains 50 balls and 150 nuts. Half of the balls and half of the nuts are rusted. If one item is chosen at random, what is the probability that it is rusted or a ball? So here there are 50 balls. So I define two events. B1, that the item selected is a ball. B2, the item selected is a nut. Now if this is first experiment, now there are two outcomes when item is selected, either it is bolt or nut. See, when item is selected, because there are only bolt and nuts, so any one of them must be selected. When we select only one item, both will not be selected at a time. So first two conditions are satisfied. Remember that there are 50 balls and 150 nuts, so total items are 200. So total cases will be 200, and favorable for getting B1, that is favorable for ball. Since there are 50 balls, that probability is 1 by 4. Similarly, probability of B2 is 150 by 200, means 3 by 4. So these are the individual probabilities of B1 and B2. Now we define event A. So let A denote the event that the item selected is rusted. So it is given that the item is rusted. So half of the bolts and half of the nuts are rusted. So probability that the item is rusted, given that it is bolt, is half. Similarly, probability of A given B2 is also half. Now here we have to find probability that the item selected at random is either rusted or ball. So I just write B1 union, B1 is bolt, union A. This we have to find. Now here, without applying this addition theorem, we can say that either it is bolt, means B1, or if it is not bolt, just see, suppose there are 50 bolts, 150 nuts, and half of the bolts and nuts are rusted. So this portion is rusted area. So this is A area, these and these. Now the item selected is either bolt, if it is bolt, okay, or it should be rusted. So rusted, in when we consider B1, then this rusted portion is also taken. If it is bolt, then it should be only rusted. So this portion only, either bolt or rusted. So we cannot consider this part two times. So it must be, it is rusted and bolt, sorry, and nut, rusted and nut. So actually this should be the probability, or we may say that it is PB1 plus this is PB2 into P of A given B2, because we know PB2 and PA given B2 also. So this way we can find, or same result can be obtained, we can obtain this as say PB1 S generalization theorem plus PA minus P of A intersection B1, PB1 plus Now to find PA. PA means, according to that addition theorem, PB1 into P of A given B1 plus PB2 into P of A given B2 minus P of A intersection B1. A intersection B1 means PB1 into P of A given B1. So PB1 into PA given B1 gets cancelled, and ultimately we get same result.